When you first learn algebra, mathematics feels rigid. You are taught to isolate a variable and lock a single exact numerical answer into place. But then, those discrete blocks shatter. Early mathematics trains us to solve for specific points. Finding x implies a static, isolated reality that rarely exists in practice. In engineering and physics, models exist across continuous, shifting domains. These ranges of safe operating conditions are defined by inequalities rather than strict equalities. Three core mathematical classes create the most complex boundaries in these domains: rational polynomials, logarithms, and piecewise modulus functions. We are going to abandon brute force guessing and build a deterministic, visual toolkit to calculate the valid domains for these functions. Mastering inequalities provides the essential logic required to map the exact boundaries of a system, preventing physical and mathematical models from collapsing under the weight of edge cases. Determining where a massive rational polynomial function evaluates to greater than 0 requires a method more efficient than manually testing an infinite string of decimals. The wavy curve method acts as a deterministic sorting algorithm that maps out positive and negative domains across a number line. Look at this rational polynomial. Step 1 is extracting the critical points by equating every individual factor to 0, yielding 2, -1, and 4. Step 2 requires plotting these roots on a number line in strict increasing order to establish subintervals. For step 3, we initialize the sequence. Because all our x terms are positive, we place a positive sign in the rightmost interval. We then evaluate the map by moving right to left across our plotted roots, checking the original exponent of each factor. Hitting the root 4 from an odd power, the sign flips, crossing into negative territory. Continuing left, it hits 2, also an odd power, flipping back to positive. But hitting -1 from an even power, the sign persists and bounces off the axis. This sequence of bounces and crosses forms a complete, continuous geometric map of the function's behavior. The wavy curve takes an infinite guessing game of decimal testing and compresses it into a finite, visually guaranteed certainty. Logarithms present a different kind of boundary. They map exponential relationships, asking what exact power a base must be raised to reach a specific value. Applying standard algebraic balancing rules to logarithmic inequalities often causes catastrophic logical failures. In these specific cases, the base acts as an operator that dictates mathematical reality. Take this standard logarithmic inequality. Attempting to strip away the logs splits the logic into two divergent paths, determined entirely by the value of base m. The first condition occurs when the base m is greater than 1. A base greater than 1 creates a strictly increasing function, preserving the inequality direction. We can safely remove the logs and state that x is strictly greater than y. Now observe the second condition, when the base m sits between 0 and 1. This fractional base creates a strictly decreasing function, which inverts the relationship between inputs and outputs. Dropping the logarithms in this scenario forces the inequality symbol to violently reverse direction. X is now strictly less than y. Regardless of the base, all logarithmic operands must remain strictly greater than 0 to stay within a valid domain. Logarithms demand we analyze the behavioral nature of the operator before we attempt to manipulate the variables inside it. The final operator is the modulus. Beyond simply removing negative signs, the modulus performs a specific geometric task. The modulus is a piecewise boundary function. It measures absolute geometric distance from an origin point, regardless of direction. Because it measures distance, we can use it to split intervals. Consider this expression bounding the modulus. Geometrically, this shatters the domain, rejecting the center space entirely, leaving two valid mirrored outer segments united by an OR condition. This spatial logic faces its test in the triangle inequality, which governs the addition of variables inside a modulus. Under what exact mathematical conditions does this inequality become a perfect equal sum? The equality condition demands that the product of x and y is greater than or equal to 0. They point in the same direction, stacking end to end so their combined length matches their individual lengths added together. When x times y is less than 0, The variables have opposite signs. They geometrically push against one another, folding back on each other, ensuring the absolute distance of their sum is always lesser. Advanced manipulation of the modulus requires carefully tracking these opposing spatial alignments and their rigid, non-negotiable domain bounds. Look at the architecture of this theoretical equation: a modulus inside a fractional logarithm, bounded by rational polynomial factors. Standard algebraic brute force fails here because the domain would be riddled with logical contradictions. By layering our toolkit, we first define the baseline continuity by extracting critical points and tracing the wavy curve. Next, we analyze the logarithmic base operator, locking in the direction of the inequality. Finally, we enforce the spatial boundaries, using the modulus piecewise split to narrow the valid intervals. Advanced mathematics functions as an architecture of overlapping logical constraints. Visualizing these complex overlapping constraints reveals the specific, safe operational ranges, where a theoretical model remains entirely valid and mathematically sound. These deterministic rules, the wavy curve, log bases, and piecewise boundaries, provide the structural logic required to calculate and maintain precise physical models.